The last problem, there's a couple of sort of applications of products of polynomials. A couple of them are volume ones. I'm not gonna. You guys can just figure those out. I want you to just think about those. I don't want to. I want to avoid with this group, too often like doing too much stuff. So where I've done it and then you don't have to think about it. So all the volume ones, I think there's 2 or 3 of them at the end. You guys will have to just kind of think about those a little bit. And it's no big deal. This one, let's just talk just for a second about this. There's an example here of, the reason I want to talk about it is because it's a pretty good problem in terms of it actually reflects what you really do with polynomials in math lots of times. So this guy, Mr. Silva, is managing this manufacturing plant and is telling us from 1990 through 2005, the number of units produced in thousands is modeled by this function. And that's something you can do pretty easily. If you have some data, some manufacturing data, you could use your graphing calculator or you could use Desmos or anything like that. And pretty quickly you could do a fit. You could do a polynomial fit. This is a quadratic fit because it's a quadratic function that we've used the data and fit it to. Remember how we did all that stuff earlier in the year with the best fit line, with linear regression? Well, it's the same exact process, only instead of choosing StatCalc 4, you choose StatCalc 5, which is quadratic regression. And so it gives you back this function. So say we also have done some research and we've looked at the data and we know that the average cost per unit over that same time period is modeled by this quadratic function, right? Well, then what would you do if you wanted to find the total manufacturing cost or production cost? If this one represents the number of items manufactured, N of X does, and C of X represents the average cost, manufacturing cost per item, how are you going to find the total production cost? Multiply it. That's it, right? All you got to do is just multiply those two together, right? And that's going to give you something kind of ugly, but a lot of times maybe you don't even have to go through the whole process of multiplying that out and simplifying, right? For example, in Desmos, you could just take this function times this function and don't simplify, or on your graphing calculator, right? You don't need to simplify it for graphing technology. It'll know what you mean, right? But the product of those two things is going to give you what you want, right? And then if you wanted to, for example, like I'm going to ask you to do, I'm going to want to know, well, actually I am going to ask you, what is the function, right? What is the simplified function? So on this one, you are going to have to go through and distribute, but it's not that big a deal. You can use a calculator to do it, where you can find out what all the coefficients are when you distribute through. Then what if we wanted to make a prediction? Let's say we wanted to use this model to predict what the total manufacturing cost was going to be for the year 2008. What would I do? That's going to be a graphing utility question, isn't it? What do you think, Tyler?
Extrapolate based on the function.
Yeah, well, so what's that mean? Let's just say we use the graph. What would that mean? Yeah. Okay, so if X represents the number of years since 1990, that would be, what, 18? Right, we just plug in, would evaluate the function at X equals 18, and we could do it right on the graph, right? It'll give us back the Y value is going to be the predicted manufacturing cost, right? Okay, no big deal. Okay, so then what about stuff like this? So the next assignment, the first group of problems is just, I'm giving you a bunch of patterns. And we can just do these together right now. You don't even have to figure these out. I'll just tell you what they are. This is what we call, and go ahead and put these in your notes. This one is called a conjugate product pattern. Okay, why is that a conjugate? Well, we know what conjugates are, right? We've done this in the past. Conjugates are just if I have two terms and they're either added or subtracted, the conjugate factor is going to be the other operation. So in this case, If we start with a plus b, I'm just going to multiply by a minus b, right? Those are conjugates. If I started with a minus b, its conjugate would be a plus b, right? What do I get when I multiply those out? A squared plus b squared. Yeah, this is what we call a conjugate product pattern. We're going to turn around here pretty soon. Thank you. So we end up then with the pattern a plus b times a minus b equals a squared minus b squared. If we're going from left to right, that's a product pattern. Pretty soon, like starting, I mean, maybe even, I don't know, like tomorrow or the next day, we're going to turn this around and we're going to do the opposite. And we're going to look at factoring patterns. So if we saw something like something of the form a squared minus b squared, and we wanted to factor it, well, it's going to be the conjugate, right? The conjugate pattern, a plus b times a minus b. And then we'd call it a difference of squares, right? A difference of squares will be a factoring pattern that we recognize. It's just the reverse of this product pattern, okay? So if you multiply two conjugates, you get the difference of their squares, always, okay? How about something like that? A plus b squared, or a minus b squared, or a plus b cubed, or a minus b cubed. Okay, these are, there's a section in our book called section 6.3, which we're going to skip. But I want to show you guys something kind of important here. We'll come back at the end of the year, and this is one I really want to come back to, because there's some interesting probability stuff that comes out of this. It's a really cool relationship, and I don't want to take the time to do it right now. But there is one thing I want to show you that's very useful. The binomial theorem, what it does is it tells you how to expand out any power of a binomial, which is just a polynomial with two terms. So we'd say something like a plus b to the n, and n could be anything. And the binomial theorem tells you how to write out each term in that expansion, right? It's pretty complicated though, and it's not something that's really necessary for us to go through right now at this moment. But there is a really good trick. There's a trick for very quickly expanding out any of the, like the first up through, let's say, n is 6. There's a really quick way of getting all those coefficients. Here's what it is. Very cool little process. It's called Pascal's triangle. So put this in your notes. This is a good one. You'll use this a lot. So Pascal's triangle, here's how you build Pascal's triangle. You just start at the top and you work your way down. You start with a 1 at the top, and here are kind of the rules for this. The outer slopes of the triangle, the sides of the triangle, are always going to be 1s, and all the interior numbers are always going to equal the sums of the numbers above them to the left and right. So for example, to there, we don't really have to do any, I mean, we can't really do anything yet. But when we get down to the third row, we get 1s on the outside, and then what's going to go in there? 2, because it's going to be the sum of the numbers above it, left and right. So what's the fourth row going to look like? 1. What goes there? 3. And what goes there? 3 and 1. You see how we're getting this? We get the 3s because those are just the sums of the 1 and 2, and then the 2 and 1, right? What's the next row going to be? 4, 6, 4, and 1. Let's go down one more row. What's the next row going to be?
1, 5, 10, 10, 5, 1.
Okay. Now you notice a couple things about this, right? Do you notice that there's some symmetry to this, first of all? Yes. Right, if we were to draw a line right down the middle, you can see that these number patterns are always symmetrical about that, aren't they? Right? Okay. What these are, we can associate each one of these rows with a power of a binomial expansion. So really all these are going to be the coefficients that go with the expansion of a plus b to the n, where the top one is going to be n equals 0. The next row is going to be n equals 1, and so forth. So those are the coefficients. So then what's that telling us? What does it tell us, for example, that what does this row tell us? So it tells us that a plus b squared equals, the coefficients are 1, 2, and 1. And what are those being multiplied by? Well, here's how you play this game. We know that they're going to be products of a and b to certain powers, and the sum of their exponents always has to add up to n. We're going to start with all of the weight shifted to the a's. So the first one is just going to be an a squared, and then this would normally be invisible, but there's going to be a b to the 0 there, which we wouldn't write. What is b to the 0? 1. So we would just say the first one is just a squared plus 2a to the 1 b to the 1. So that would just be 2ab, right? Plus 1a to the 0 b squared. Now that's not how we would write that though, right? How we would write that would just be a squared plus 2ab plus b squared. Well, that looks familiar. You knew that expansion already, right? But it's consistent with Pascal's triangle, right? So then what if we went down to this bottom one? What's that telling us? It's telling us that a plus b to the n equals what? What's the first term going to be? 1 a to the 5th, right? Does everybody see that? So there's the coefficient, and all the weight of the exponent is pushed over to the a's. As we move from right to left, the a's are going to incrementally drop down. The exponent drops down by 1 each time, and the b's are going to increase by 1 each time, so that their sum is always 5. So what's the second term going to be?
5a to the 4b.
Right, so 5. The a's drop down to a to the 4th, the b's move up to b to the 1. Right? Plus
7a cubed squared.
See how that works? Plus 10 a squared b cubed plus 5 a to the 1 b to the 4th, and then the last one. That makes sense? Okay, let's talk about this at a little deeper level for a second. There needs to be an isotropic nature to that kind of an expansion, meaning a and b should not be, there should be no preference for the a or the b, right? Does that make sense? Because isn't addition commutative and associative? So I should be able to interchange the a and the b, and it shouldn't change the pattern. If it did, something would have to be wrong, wouldn't it? Everybody agree with that? Is that just intuitively, doesn't that seem right to you? So then, does it make sense now why these coefficients have to be symmetrical, right? You see, because what if I put the b first and the a second? The pattern should still hold, right? Everybody get that? Okay. Questions? Does that make sense, how we get that? So it just takes a second to crank out this Pascal's triangle. If you're doing anything beyond n equals 3, we probably don't normally memorize those because we don't use them that much. Yes, ma'am? Yeah, absolutely. You could go down to something like, say, n equals really 7 or 8, and this would be a pretty easy way to quickly, without having to go through the arduous process. Can you imagine how bad that would be to do something like a plus b to the 7th? I mean, actually multiplying that out by hand would be, no one wants to do that. That's going to be terrible. You're going to have to do pairs of products, a times b, simplify, distribute a times b, simplify, distribute a times b, simplify. That would take a long time. No one wants to do that. So this is an easy way to just get a shortcut to where you know what the coefficients are going to be and you know the pattern, right? But the first, those don't even, what's a plus b to the 0? Anything to the 0 is 1. And a plus b to the 1, well, what's anything to the 1? Just itself, right? So that's just 1a plus 1b. So those don't even really, they don't mean anything, they're just given. But these two, we use so much that we just want to memorize those. And all you need to know are what the coefficients are, right? It's just 1, 2, 1 or 1, 3, 3, 1. And that allows us to very quickly expand out a binomial to the second or third power. Okay, let's take an example. So what would we get then? We know what the coefficients are for a plus b cubed, right? They're 1, 3, 3, 1. So what would we get, for example? A lot of times this is listed as a separate expansion, but I hate to do it that way because it's just more to memorize. And you've memorized things, that's a really low level of learning, and you're going to just forget it, right? So instead, memorize this pattern and just apply it to a minus b cubed. A minus b is the same as a plus what? Negative b, right? So the same pattern holds, doesn't it? So if we want to figure out what this expansion is going to be, we know the coefficients are still going to be 1, 3, 3, 1. What are we going to get for the powers of a and b? What's the first one going to be? A cubed times negative b to the 0, but anything to the 0 is 1, right? So it's just going to be a cubed. Okay, what about the second one? Okay, good. I'm going to get an a squared, but I'm going to get a negative b to the first. So a negative number to an odd power is what sign? Negative, right? So that's going to end up making that term negative, isn't it? Right? What about the next one? I get 3a to the 1 negative b squared, right? And all I'm doing is I'm just thinking of this a minus b as being an a plus negative b, right? And using the pattern that we've already established. And then the last one's going to be plus a to the 0 negative b cubed. So if I simplify that, the first one is just a cubed. The second one's going to be minus 3a squared b, because the negative part is to an odd power. Next one is plus, good. Because the negative one is being squared, it's always positive. And then the last one. Okay, and that's something you're going to notice when you go through these expansions. Whenever you're doing an a minus b to some power, all it's going to do is just, you'll notice the pattern is always going to be there. It's just going to be plus, minus, etc. all the way through. Okay. All right, so let's just try a couple of these then. So if we scoot down to where we're actually applying these things, rather than having to multiply that whole thing out, what's the answer going to be? What's a and what's b there?
Negative 5x.
Okay, so a is like negative 5x, and b is 1, right? So we're going to do, so it's a plus b times a minus b, right? So what's the answer going to be for this one?
A minus q times.
Yeah.
5x squared minus 1.
So, yeah, I've got to do that whole quantity, right? There's my a squared minus b squared, right? What's that going to give me, once again?
25x.
Yeah, so I'm going to get a positive 25x squared minus 1, right? Okay, everybody agree? Okay. Okay, how about something like that? That's easy, right? What's going to be my pattern for that one?
1, 2, 1.
No.
1, 3, 3, 1.
1, 3, 3, 1, because it's going to be a binomial cubed, right? What's a? 9x. What's b? 10, right? No big deal. I'm going to skip up to the next page, and we'll actually maybe do this one. So what are the coefficients? What coefficients? 1, 3, 3, 1, right? Because it's a cube. And what's A? What's B? Okay, so then we ought to be able to just write this one down, right? So we're going to get 1, what? A cubed, right? So in A you said was the quantity 10x. So the first term is going to be 10x cubed, right? Plus 10x squared times minus 1 to the 1. So what's that make the sign of that term? Right? Everybody agree? Because I'm going to be multiplying A, which is 10x squared, times B, which is negative 1, right? 10x quantity squared times B to the negative 1 to the 1, which makes that one negative. Everybody with me? Here, I'll tell you what, let's not do it that way. Let's just write it as plus 3 times 10x to this 2 times negative 1 to the 1, okay? It's going to make that term negative. Plus 3 times A to what power? The 1 times B to the 2, right? Plus 1 times B to the 3, right? And that's just going to give us, if we multiply all that out, what is the quantity 10x cubed?
1,000.
Okay, good. 10 to the 3 times x to the 3, so it's 1,000 x cubed. Here I'm going to get 10x quantity squared is 100x squared times 3 times negative 1 minus 300x squared. Everybody agree? Okay. Plus 3 times 10x to the 1 is 30x times negative 1 squared is positive 1, right? So plus 30x, and then finally minus 1. Negative 1 cubed is negative 1, so that's my answer. Right? Get it? No biggie. And that's it. That's pretty much it. Then the last two are going to be probably, yeah, so these are easier. These are just A minus B, A plus negative B squared. Right? That's no big deal. Well, you already know that one. It's A squared plus 2AB plus B squared, right? Where A is 7x and B is negative 1. Okay? Coefficients 1, 2, 1. You already knew that one. All right. You're set.